So we have been seeing the linearity constraint of the system from last class onwards. So let's quickly review what we did and then we'll go back. Towards the end of last, we thought that in general in analog systems there are several different ways of characterizing nonlinearity, right? Many of them will not work for us for various reasons. For example, looking at harmonic distortion will not very often work for RF systems because of the fact that many of your circuits are narrowband. Whether it's filters, the antenna itself has a frequency response, the circuits themselves will have strong frequency responses and so on. Okay, so if you look at the THD of the voltage, it will seem very, very low, even though your system looks very, even though your system is very nonlinear. Okay, and it turns out that if you take such a system and put in a communication signal, a modulated, it will cause trouble. Okay, it will cause degradation of the signal. Okay, so we need to find out a better way to characterize it. So one important way on the transmitter side is to use the 1 dB compression point. So what we said was you want to find out the maximum power that can be squeezed from a circuit. This is normally on the transmitter side, not on the receiver side. And in that case, you really want to squeeze out as much power as possible because the remote guy needs to receive as large a signal as possible. Okay, and that is characterized by some standard value called the 1 dB compression point, where the actual power from the circuit reduces from the ideal power expected from the circuit by 1 dB. So the difference between the actual and the ideal is 1 dB. Okay, and if you take the x-intercept, that is the input referred 1 dB compression point, not the x-intercept, the x value, the y value is the output referred 1 dB compression point. Okay. Unfortunately, this is still not good enough for a receiver, because for a receiver, very often you will not be having such a high input power so as to saturate the receiver. Okay, at least not saturate the front end. By the time you hit the end of the receiver, you will indeed be saturating. You should be. Okay, so that you get enough gain through the receiver chain, so that at the end you have a sufficient signal going into the data converter. Okay. So in the case of the receiver, you don't rely on the 1 dB compression point directly. Now let us look at what happens in the receiver. So maybe you have multiple guys, mixers, filters, etc. Okay, so the signal here is small, but one other thing that you see is that coming right at the input of the receiver, the antenna maybe have some bandwidth, but what you will very often see is a combination of signals, because this is your desired signal. Okay, very often right next to it you may see some other undesired signal which is right. For example, imagine you are operating your phone next to a microwave oven. Imagine you are trying to laptop neck while running the microwave oven to heat something, right? So the microwave oven is putting out, there will be some leakage power. The microwave oven power level is in hundreds, if not hundreds of watts, if not kilowatts. Okay, there will be some 0.1% of that, 0.001% of that leaking out. You know, it's very well shielded, but some small amount will be leaking out. That amount itself will be many orders of magnitude larger than the signal you are trying to receive. Okay, whether it's a cellular signal, whether it's a Wi-Fi signal or something else. Okay, and very often you may have multiple unwanted signals. which are much larger than your desired signal. Okay. In fact, such a signal is often called a blocker or a jammer. A signal which is so large that it is going to prevent you from receiving is called a blocker or a jammer. Okay. If you are trying to build, the reason for that is if you are trying to prevent some guy receiving a signal, one reliable way is to find out the approximate frequency range and put out something so large that it's going to completely swamp out whatever signal he's trying to receive. Okay. The reason is because none of the receivers are so narrow band that they will be selective only to that desired signal. Okay. And we will see this when we actually go to your RF systems a little bit later on in the course. Most probably once we finish the LNA portion, we'll have enough to do your LNA project. I'll come back to RF systems. Okay. The typical kind of frequency selectivity you will need, okay, is anywhere, you are typically operating in the gigahertz range, 2-3 gigahertz range. The selectivity that you will need is anywhere from kilohertz to megahertz or maybe tens of megahertz nowadays. Okay, that still corresponds to a Q of several tens, which is very high. A Q of several tens is actually very high Q. It's a very high Q system. You would normally see in practical systems. In practical systems, you will see Qs of a few single digit numbers. That is probably the kind of Q you will see, effective Q of your receiver. Okay. So, this is a problem. You want to actually figure out how to characterize this system, right? A receiver system where you're trying to receive something very small and you could have very large signals that are causing trouble for you. Okay. The standard way of doing this, the second thing is to take care of the earlier point. You need to consider that your system is narrowband. Okay. So, instead of putting in just one tone, we will put in two tones into the system and see what happens. If you put in one tone, you will see what we have seen before. You will see compression. You're putting in one frequency, you're looking at the other frequency, right? And you see what happens, that will give you compression. Okay. If you look at the relative value of the other tones, other harmonics versus your fundamental, it will give you the harmonic content, harmonic distortion. What we are going to do is something totally different. I am now going to take this system and put in two tones, and by convention these two tones are equal amplitudes, okay, spaced apart by some small delta omega. Yes. Sinusoids. Just tones. Right? A tone is basically a single frequency. This is a sinusoid in the frequency domain. Okay? You have not heard this term tone before? A single tone signal, a double tone signal? Okay. So, thanks for telling me. So, a spectrum that has literally an impulse at a particular frequency is very often called a single tone signal. If you put in something like that into a system, you are said to be characterizing the single tone response of the system and so on. A tone is a frequency component. Okay? Realize this. Okay. Thanks for telling me. Huh? So, these can be interference tones. These can also be in general, yes, they were originally meant to characterize interference tones. Okay. But, in general, if you look at modern communication, you also have, how many of you are taking communication, digital communication and wireless communication, cellular communication? Any of you? Okay, somehow only one of you or two of you. What you will find is that if you take those courses, what you will find is that modern communication signals are actually composed of a single signal but a composite of multiple signals, right? Many modern high signals use a particular type of signaling called OFDM. I don't know if you have heard of this term before, OFDM. So orthogonal frequency division multiplexing. Okay, orthogonal frequency division multiplexing. So this is something, the OFDM was discovered probably about 20 years ago, 20 years ago. Okay, and now it has become so powerful that it is being used in a lot of high data rate systems. Okay, the basic idea is very simple. Okay, now we are taking a very strong right turn into communication systems, but that's okay. If you remember, yesterday we talked about, in the previous class we talked about ways of doing analog communication. Okay, we said you can do analog communication. Let me try to find that. I have it here. I think this is the one. If you remember, we said that signal can be sent as phase modulation, frequency modulation, or amplitude modulation. Right? These are the most common ways, in fact probably the only ways, right, of communicating. Right? Now in modern systems, we are looking, this is analog communication. If you look at modern systems, you can do phase modulation, frequency modulation and amplitude modulation in the digital domain. Right? You don't need to do it in this form. Right? What you do it is on the digital, you perform PM, FM or AM and then convert that to analog using a DAC. Right? If you look at the DAC information, of course the information is contained in the amplitude, phase or frequency, but you will not be able to directly demodulate it until you use the digital analog to digital converter at the end of the receiver chip and then apply appropriate demodulation techniques in the digital domain. Does that make sense? I hope it does. For now it will have to do. Okay. Otherwise we will now be not doing nonlinearity but something else. Okay. So if you were to do that, okay, that would be AM, PM or FM, either in analog or digital. Now in OFDM, what you do, take a whole bunch of AM, PM or FM modulated signals and create a composite of them. So what you do, so let me see. I am now going to split my, let's say the signal occupied some frequency, I don't know, 1 megahertz. Let us say this was the bandwidth. Hypothetical. I am going to split this up into a whole bunch of sub-bands and in fact sub-carriers. So what will happen, instead of looking at the signal as a single analog signal having a bandwidth 1 megahertz, what you will find is that there are lots of sub-carriers periodically spaced. Each one of these has some modulation around it, carries some independent modulation. Okay, and you create a composite signal. Okay, and it turns out that if you choose the subcarriers carefully as well as perform some intelligent DSP, right, these subcarriers are in some sense orthogonal to each other. Okay, that is the best I can do for now. That is where the orthogonal portion comes from. You figure out signal processing techniques to keep the signals separate from each other. Naturally, if you just randomly assume that these signals were not separate, they will mix with each other in the frequency domain. Naturally. Each one of these has some frequency content, right? And they will mix with each other. But you can make sure that they do not mix. That is where the orthogonal portion comes from. Okay? If you do that, you will get a composite signal which consists of a whole bunch of subcarriers. Now, why do I bring this up? The reason is very simple. If you try to send such a composite signal into your receiver, you could in fact have interaction between the subcarriers, not just between interferers. Okay, that is all I mean. Right? Here we have tones omega 1, omega 2 which are interferers, and we are going to find out what happens, how they interact with each other when they go through the system. But it is indeed possible that they are components of the signal themselves. Right? I think that's a long-winded way of kind of answering your question. Now, it is also not necessary that if you take a real system, it is not necessary that the two interferers have the same amplitude. Right? But for ease of definition of ways to characterize the system, we will say that the system is characterized with two signals of equal amplitude. Right? You want to compare two systems. You may have systems with different gains, different bandwidths, etc. But if you want to compare the noise performance, you compare the input referred noise sources. This is something like that. You figure out a standardized way of comparing the performance. And that is what the way you do that is by characterizing the system with two equal sinusoids. Okay? I am now going to take this system and send it through this. So let us see what will happen. We'll take a generic system. We'll see. I think I don't know if we'll get all the way through the analysis. Let us say I have an amplifier. Okay? It is a weakly nonlinear amplifier. Okay? So that its input-output response. So if I give x of t, y of t can be written some, let us say some alpha 0 plus alpha 2 x square of t and so on. Plus alpha 3 x cube of t plus so on. Okay? If it's a weakly nonlinear system, alpha 2, alpha 3, etc. will be small, relatively small. And they will, if it's weakly nonlinear, hopefully they will all start reducing. As you go to higher and higher alphas, the values will keep getting smaller and smaller. Okay? For the purposes of this discussion, I will truncate it here to a third order nonlinearity. So now what I am going to do, I am going to say the system is weakly nonlinear. I am going to assume truncation of higher order nonlinearity, so I am only going to consider nonlinearities up to the third order. Into this system, let us say I put in x of t, some cos omega t. Right? What will happen? So first are alpha 0, alpha 1, alpha 2. So this is the output DC component. This should ideally be small signal gain. Correct? Alpha 1, if x of t was extremely small, I expected only alpha 0 plus alpha 1 x of t. Correct? Okay. In fact, I'll use this also because I'm going to need it. I'll assume input is a cos. Okay. So, alpha 0, a cos omega t plus okay. Now, as you can see, I now have unexpected terms cos squared omega t and cos cube omega t. What do I do with these? What is cos squared omega t? If I were to decompose it into cos omega t and cos 2 omega t, what will it be? One plus 1 plus cos 2 omega t by 2. Okay? Okay. Let's see, if you put in a narrowband signal, if you put in a single tone, the second order nonlinearity is now giving you a DC component and a second harmonic component. Have you seen analysis like this before in signals and systems? Where you had a nonlinear system and you put in a single tone and you found out the... Did you do that in signals and systems? No, you did not. Have you done this anywhere in any other course? No, is it? Okay, we'll do it now. That's okay, we'll do it now. Okay? What about this guy here? Cos omega t. 3 cos omega t minus cos 3 omega t. Is that all? Plus cos 3 omega t. He's saying plus, you are saying minus. Which is it? Which is it? Plus. Okay, and something else is missing. Divided by 4. Okay, so it's 3 cos omega t plus cos 3 omega t by 4. Okay, what is this telling you? If I had a third order nonlinearity, it is changing my fundamental. It is also changing my, it is also causing a third order component. Okay, now you can now extrapolate this. Okay, if you had a fourth order cos power 4 omega t, right? You can now imagine that it will affect your DC value, second order value and your fourth order value. So it will basically change your DC, it will add add something to the cos 2 omega t term, it will also cause a cos 4 omega t term and so on. So every even order nonlinearity will affect the even order terms. Okay? Every odd order nonlinearity will affect the odd order terms. Okay? Why does this matter for us? If I were to write this, okay, y of t now, I'm going to write it in the standard form where I'm going to group DC terms first separately, fundamental terms separately, etc. What is the DC term? Alpha naught plus alpha 2 a squared by 2. This is my DC value. Plus alpha 1 plus 3 alpha 3 a squared by 4 times a cos omega t. This is correct. Alpha 1 a cos omega t, 3 by 4 alpha 3 a, correct. Okay. Have I missed something? Is this okay? Plus cos 2 omega t plus 3 alpha 3 4 okay? I've just written out those terms. DC, fundamental, huh? There's no, oh sorry, thank you. There is no 3 in the last one. Yes, perfect. Okay. Now, you should also realize, just looking at this, if you have a weakly nonlinear system, alpha 2, alpha 3, etc. should be decreasing. They are all getting multiplied by a squared, a cubed, etc. Okay, if it's a weakly nonlinear system, they should not be affecting you when alpha, when the input amplitude is small or, medium signals. Only when you go to really extremely large signals, they should start affecting you. Right? That is the definition of a weakly nonlinear system. And that's why you assume that alpha 3 is much smaller than alpha 2, which is much smaller than alpha 1, etc. Okay. Now, not come to the two-tone at all. This is just for the single tone. Most probably two-tone we'll do next class. But just wanted to point out, for the single tone, couple of things you need to remember. Okay. This term here is actually changing your DC value. Okay. What that means, that if you had a system with even order nonlinearity, and you tried to send us somewhere in the chain, it had baseband content, right? A cos omega t is the RF signal. But somewhere along the chain, if you had baseband content, this is now changing the baseband content. I hope you can see that. Because this DC value, so imagine I now have a differential amplifier. Alpha naught should have been 0. But it is not. I am going to get alpha 2 a squared by 2 as the DC value. It will look as if the system has a mismatch. Right? Because of the second order nonlinearity term. Okay? Now, what about the other guys? Look at this guy here. What is this doing? The gain of your fundamental. You expected the gain to be only alpha 1, which is still true at small signals. Imagine you put in extremely small a's. You can now neglect the second term. Okay, it is only alpha 1, a cos omega t. But now you start increasing a. Okay, you can see that the second term eventually will start dominating the first term, because the first term is alpha 1 a cos omega t. It is linear a. The second term is, I think I have made a mistake here. It should have been a. Three alpha 3 a by 4, because there is an a cos omega t outside. Isn't it? Is this correct? Oh, sorry, this is correct. Okay. Because of it's coming from the cubic term. Okay. 3 alpha 3 a squared. So, the non-ideal term is actually increasing as a squared. Okay. Whereas the other term is constant. So, if you start seeing higher powers, you will see that the gain of the fundamental itself is changing. What does this refer to? This term? This term here, what is it kind of referring to? Something we have seen before. Compression. Right? You expected it to be a linear. You are now in this curve, P out versus P in for the fundamental. Okay? Ideally, if alpha 3 was 0, you should have just seen a straight line. But because any nonlinear system will have alpha 3, you will start seeing compression. So what does that mean also? It means the second thing. Look at the term, second term. The second term is 3 alpha 3 a squared by 4. Okay? That is always greater than 0. So normally, if you have compressive characteristics, you expect alpha 3 to be negative. Okay? Please note that. let me also tell you at this time, it is possible to build amplifiers with alpha 3 being positive. What will happen then? If I plot P out versus P in, this is my ideal curve. Okay? If I plot P out versus P in, this is compressive characteristic. What will happen? We'll start doing this. Okay? This is called gain expansion. The other one is expansion. This is gain expansion. You will see this fairly commonly in power amplifiers. Rare in LNAs, but fairly commonly in power amplifiers. Okay? Now what will happen? Will it continue to increase? So remember that P in is a function of A cos omega t. So literally you are varying A. And the second term is 3 alpha 3 A squared by 4. A increases, it's parabolic, right? So it will increase, right? This is a log-log plot, right? dB versus dB. So it will go up. But can it continue to go up? Huh? Exactly. So what will happen? Obviously, fundamentally, you know, the amplifier cannot swing larger than the power supply, right? So when you actually put in even larger A's such that the second order the third order term seems to be folding back and causing the fundamental to increase, eventually you will become so nonlinear that the fifth order term will come back and so on. And the higher order terms folded back to the fundamental will force the curve to move back to some flat region. I'll just say flat region, okay, because this is the output power, so it can increase beyond a certain point. It may do this. It cannot do this. Okay, it cannot randomly increase. Okay, so this is possible, but eventually it has to saturate. Okay, whether it's gain compression or gain expansion, it will eventually saturate to a power which is often called Psat, or the saturated power of the amplifier. In either case, okay, in the compression case it would do this. In fact, in the compression case, it may do this. Because Psat fundamentally will just be limited by the supply rails. Maximum swing you can get. I think we discussed this very briefly last class. You can extract out of an amplifier will in the end be limited by power supply and ground, come what may. Okay? So, as you can see, even if you put in just a single sinusoid, you can see all the compressive behaviors. Compressive, expansive. So, you'll change the fundamental, second harmonic, third harmonic, etc. Okay? So, literally, if you put in a single tone into frequency domain, if you put in omega, what you will get at the output is omega, 2 omega, 3 omega, etc. Okay? This is often significant if you don't have a strong frequency dependent, filter or filtering response following your amplifier. For example, if you have a power amplifier driving an antenna, the antenna will have some frequency response, but it's very possible that it does not have a very strong frequency response such that the second harmonic is knocked out enough. Okay, you will be interfering with somebody else using the band at 2 omega. It would be a problem. You will be forced to deal with this. Okay, any questions so far? If not, I'll stop here. If possible, try to figure out what will happen if you put in to the same block, to the same nonlinear block, if I put A cos omega 1t plus A cos omega 2t into this equal to what? Okay, we'll assume that omega 1 minus omega 2 is some delta omega, or omega 2 minus omega 1. We'll assume omega 2 is the larger frequency. Is some delta omega. Okay, so we'll stop for today's class.